Okay, ini what we stopped yesterday at the beginning. Actually, kita dah buat exercise. So what we say as linear expansion. Yeah, we have what we call linear expansion. This is the main concept under what we call thermal expansion. Thermal expansion. So our thermal expansion, we have this one. What we call linear expansion. We have also area expansion. And then we also having volume expansion. We have three kind of expansion. Okay, but the main one is what we see as a linear expansion. Okay, an object at least is 3 dimension. Okay, the volume expansion will be taken into in our discussion too. So this is a 3 dimension. Okay. So in our case, again, the model is what we call as a rod. Okay, of course there will be a it's a 3 dimension. Okay, but anyway, we focus on along the length. Okay, so we see as L0 initial one. Though this is the initial. Okay, initial length. Okay, at room temperature usually we see as at room temperature. Since at room temperature, what we see yesterday is we have what we call our reference in terms of what we call alpha. Okay, so we have some alpha. Okay, at using at room, also at room, since our consideration during thermal expansion, the temperature change is not so big in way that in practical this solid, this is in solid form, it's not a change what we call as the state into liquid. Immediately still solid, still remain solid before and after. So this is after we heat it, after we give the heat. You mean that what we do is we apply heat. Here we apply heat, some amount of heat, which we will be able to determine this heat. So the symbol is heat. So we apply the heat. Okay, so what will happen? It will expand. Okay, expand by delta L. Usually this is what we see if the temperature is T here is bigger than the T0, bigger than T0. Okay, it means that higher temperature. Of course, if we say heat is hot, it's hot. So what happened? The solid will getting hotter. So what happened? It will expand by delta L. So we be able to describe this delta L expansion in form of a fraction length, change of length, proportional to the temperature change. So from there we have what we call the alpha, the constant. So this alpha, we can get it from the table. I think your text have this table, what we call alpha. So you can have that alpha, the table, as I mentioned yesterday. So you can be able to have this is the main concept. We have a equation that always used dalam problems. So this is the very important equation. Everybody must know how to use it. And we have another equation that is saying about new length. This is the one that we say we can have the final length here. This final length. So actually is the addition of the delta L. So you mean that L0 plus delta L. So this is at least L0 plus delta L. So you have that is what we call the total, or the new length. The total, or both initial, and also the expansion delta L, so that you can have this form. I think this is already put in the bracket. Anyway, importantly to know what is your delta L. This is the equation. So you can see your text. I want to proceed further before we go on what we call area and volume. Just want to highlight about the alpha. Is I think quite similar in your case here. So the alpha that we call alpha, this table is for solid. All are most I mean, on the left is a solid. Okay, this is a solid. This is for the solid case. Okay, for the solid we have what we call just now we call the linear expansion coefficient. Okay, is the constant. Okay, so this constant, okay, but is given here in unit of degree C. So when you solve problem, okay, your delta T, okay, when you see delta T, you can use in degree C. Okay, no need to think of Kelvin, but actually we don't worry if you want to use or in terms of Kelvin, no problem. Okay, because the increment of the change of whatever in Celsius equivalent to the change in Kelvin. Okay, so that is what I told yesterday. So what actually in your calculation, okay, based on your what we say as delta L, okay, the expansion, you can use either Celsius or Kelvin, but because this table are using per Celsius, okay, per Celsius, limited using Celsius, don't worry on that. It happened in Kelvin. So you can see the unit here is a power of -6. Most of it power -6. You mean that the expansion actually is not really significant for solid. Not really significant. You don't think that it had to expand per longer in the way that you expected. It's very small. It's a very small expansion. Anyway, it's very important to us to know this. So you can see the one that what we call metal. Okay, all these are metal. Okay, the first three are metal. You can see is higher than non-metal. You see, this is non-metal glass. This is a special to say about glass because glass also can expand. Okay, so you can see there is a higher than the non-metal, but we have also at the bottom here we have another metal should be okay. These are in the box. Okay, it's a metal. So metal is okay. You have a higher than the non-metal such as glass. We also having concrete there. Okay, also is a concrete actually is a mix of cement, okay, with steel. Okay, so we have such value here there. The 12 also higher. So this is all the value of what we call the coefficient of linear expansion. And I told that, okay, yesterday we can have also what we call as a volume expansion. So volume expansion, after this I will say about that, okay, based on the linear expansion, we also having the coefficient using symbol of, what is the symbol for volume expansion? Is a beta, right? Plus, it's beta again. You can see your text, right? So the beta here is 10 power minus 4. And I told yesterday, okay, this beta, okay, it means higher than is 100 times, 100 times larger than the solid. So the liquid here and gas, liquid and gas is I think you can see gas here. Okay, there's a gas there. Okay, this is gas. Okay, you can see, okay, gas is more higher, 10 power minus 3. It means that gas can expand more than the liquid, okay, as compared to solid. Okay, so this is to show that, okay, expansion in terms of volume expansion apply much on higher than for liquid and gas as compared to solid. Okay, okay, this the thing that you need to highlight. But to say that, okay, in your table, in your text, okay, in your text, you can see you don't have what we call as you don't have the what we call as the linear expansion. It means that alpha is not exist for liquid and gas. Okay, it's not exist. But for solid, we have both. We have both. We have both linear and volume. Since for solid, okay, we can expand 3-dimensional. Okay, 3-dimensional, and we may prove from our analysis, okay, where this beta, okay, equal to, okay, this beta is equal to 3 alpha. Okay, 3 alpha. We don't do the analysis, okay, where at least you times 3, it will be approximately, okay, close to what we call 3 alpha. for solid. Okay, so this is a guideline. If we know what is the linear expansion for solid, we'll be able to know the volume expansion in terms of a three-dimensional expansion. So this is to highlight on that. But we don't have the linear expansion for the liquid, since it don't have shape, it don't have the linear expansion. So only having the volume expansion. Okay, just want to highlight the volume expansion. I want to show that just now my table is not using this power of -6 kan. Okay, cuma now is to compare both. So in -6, but you see the value in front is 1,000 times. Betul tak? I told just now is 100 times or and be very high. So yeah, meaning the same lah, meaning the same. Nanti you think of this -4, but actually we can change to -6, so that this number will become bigger. Okay, anyway, it's larger than the linear expansion. Okay, from your notes, we have all your analysis on what we call as a volume expansion. Where we can define as a delta V rather than using your what we call as an L and L naught. Okay, now change to V naught. Okay, you can see for the volume. Okay, so just change the symbol. Okay, so we'll be able to do that. To prove that the beta is equal to 3 alpha. So that one I don't want to discuss further. Yeah, and also kalau we have a special case. Such as a thin plate, is a what we call plate, such in form of two-dimensional, or this you can call it this, whatever, like your what we say as let's say your shilling, whatever. Okay, so this is the equation using another symbol that called what we call as a gamma. So gamma. Now it's area, so the term area is A, so you change to A. But this is a special case. We have a problem for this one. After this, for solid. So when we apply this gamma is equal to alpha. Okay, so this is a special case. Usually we discuss on volume expansion, but there's a special case where we have to alpha. Actually, all these gamma. And also your beta, okay, all that, okay, at least approximation, close to your value of what called 2 alpha and 3 alpha. Okay, finally we make it straightforward, 2 alpha and 3 alpha, and 3-dimensional 3 alpha, 2-dimensional 2 alpha. Okay, based on the linear expansion for solid. Okay, class, is that clear? Everyone clear? I'm repeating everything back.
Clear.
Okay, this one is the one that kita dah buat yesterday. So I think I have in my slide, where we have the tape. This is a PBL. We done it. Okay, kita buat. Kita buat semalam, tapi anyway, I just want to show that one lah. Okay, this is the case. The case where we have the thermal expansion for what we see as a PBL, the first PBL. Yes, okay. This is centimeter, right? But mine is centimeter, but the note is meter. Only the unit different lah. Okay. Tapi ini soalan lain, different question, different question. Tapi I can make it, let's say this another problem, this centimeter. So make sure that you kena tengok cuma dalam this what we call linear expansion, okay, you can remain the unit centimeter, okay, but the PBL is 50 meter, okay, but now is with also Celsius, okay. So of course one is a T naught, and then it's a final temperature, okay, getting hotter, it will expand, okay. So this is a T, okay, also in Celsius, don't worry, cuma answers tu can remain in centimeter. Immediate it will expand. Is for aluminium, okay, in centimeter. You can remain the unit in centimeter. Okay, for this example, is using centimeter. In your PBL, you are using meter. Okay, so expansion here is to show that this is your expansion. This is your delta L. Okay, So it's asking you what is your final length. This is the final length, right? So where L equal to delta L, you need to use to find delta L first, then you can plus with your L naught. So the delta L is very small, yeah, it's very small. So this only up to 35 that you see, yeah. Mine in my slide here is up to 120 that you see. High temperature still remain in solid, yeah. Still remain in solid, okay. So expand a little more significant, 0.12 centimeter there, yeah. Okay, so this is what we call thermal expansion. Okay, class. Hopefully that clear. And I can proceed with PBL 14.3. Okay, you notice PBL 14.3. This problem, okay, is saying about what we call a glass flask. This is like a beaker, or in terms of container. You can think of like that. It doesn't matter I put it in this way. And this is what we see as a 200 centimeter cubic, 200 centimeter cubic. Volume, this is a volume, centimeter cubic. As I told, our problems usually not worry about the unit, especially for the unit for the expansion. You can remain the same. Why? Because if you use that one, okay, the unit, we can remain our final answers with the same unit. So this is 200, yeah. So we can think as a V naught, as V naught. Okay, it's the volume that it can fill up, can be filled up to maximum. So what we say that if we fill up fully of liquid, okay, the glass is solid, it's solid, but you fill up with a liquid that called, here is the mercury. Mercury is we see as a Hg. It's a metal, but the metal, all this metal, but this is a liquid. Mercury at room temperature is a liquid, such as your thermometer, using the vial, in terms of the glass thermometer we have in the lab. I think you are using that one, two, in the lab. The glass thermometer in terms of using a mercury is a liquid at room temperature. I mean, at room temperature, you can refer at room temperature. Okay, we have the value that given in your table. If you refer, it is according to you can see your table. It is as what we call as the beta, the volume expansion. Okay, for mercury is given as beta, but this solid is given by in terms of alpha. Okay. So you're saying that if we fill up to the maximum, it means that also having 200 centimeter cubic, because fill up to the brim, this is to say this is a maximum. Right? It means equal volume. Okay. And what happens if we apply heat, amount of heat, okay, and raise up to 100 degrees C, mean that this is initially at 20. Okay, at 20 initially is T0 is 20. Okay, T0 20. Then we heat it up, reach up to T that is equal to final, that is 100, like a boiling per temperature for water. 100. So we increase it up to 100 degrees C. So there will be an expansion for both. You mean that the solid also have an expansion. So we have delta L. If let's say you want to see about expansion, but anyway, since we say this is a solid in terms of volume, okay, because we want to see about the volume of the flask, okay, so we can say delta V. So we need to use here as a volume, okay, for the case for the glass, although it's a solid. So there is a beta, okay. Okay, we use beta. There is okay, 2 alpha. So using 3 alpha. Okay, we have the glass, right? Not alpha. This is so 3 alpha. Okay, see the glass, for the glass, you have that dalam here given as 0.4. You see that is using Kelvin, using Kelvin. Not as dalam you punya notes tu kan, notes tu gunakan apa 3.3 kan, tapi gunakan whatever given here lah. This is the alpha for the glass that you use inside using Kelvin. But anyway, you can use it, no problem, even though in Kelvin. As I told you, can use both Celsius and Kelvin together in that way. Both can be used, since the increment are the same. So you can use a 3 alpha. This is the alpha. So you can get the volume expansion since it fill up the volume. So you can say that this for the glass. I put G glass for the glass. So you can find this one. Apply the formula again. Apply the formula, right? So you use the beta for the glass, then V naught for the glass. There is also 200, Then we have delta T. So what is your delta T there, class? What is your delta T, class? Please respond. Are you there? So you are typing there. 80, right? Okay, 80. So you get your value of the change of the glass volume. Okay. Then you can do the same. What is the expansion for your mercury? Because this is the principle. Because now is to say, okay, what happens if you heat up? So there will be expansion for mercury. You do yourself similarly. So you will have 2 answers. One is for this is for the first part is for glass. The second part is for your mercury. Okay, you see that there will be overflow because you see that there will be an overflow of mercury. You mean that? Okay, it's saying that the mercury will be overflow. Anybody can tell me why mercury overflow? Spill lah, dia akan spill out. Overflow you understand kan? Dia macam dia overflow, right? Dia akan out lah, out from the getting out. I mean that is an overflow. I mean that some mercury will be out from the glass. Why? Why it overflow? Okay. You'll be able to see that this delta V is larger than delta glass. You will discover your answers. The delta V for mercury is higher than delta V for glass. Okay, that's why this is the reason why we can have the overflow. So I let you to find these 2 values. Okay, and you'll be able to discover the overflow is the difference between the mercury and the glass. And the difference between the mercury and the glass. Okay, because initially both are the same. Of course, there is the same volume. Okay, if you add up, there is you can get the final volume. But anyway, since both are the same, so you can use the change of the volume so that you can get what is the overflow. So this is I do it as your exercise. Okay, class. So answer is given there. But actually, I want to remind because I have comment last time from other groups, from previous group. My way of teaching solving problem. I said I not really prefer to have answers. Answers, because the answers actually will put yourself not confident on your solution. How you solve the because you want to solve the problem. So use the basic concept. As I use here, what I'm saying as what we call the volume expansion, the concept of thermal expansion. Then from there, you start to think of to tackle the problem, based on the concept that you solve. Answers for me, I want to say, answers for me, when you learn physics, is the final one. For me, it's not really important. I want to see this solution. But anyway, kalau you have similar final answers, I can say That should be that way lah. You don't make any miscalculation, or there is no mistake of your error from your calculator. Maybe the error come from the calculator. Maybe the error come from you. The calculator will not make error, but maybe it can make some some not error. Yeah, it's because of some technical from the calculator. But the writing, I mean, the problem that you solve, show that you are really get to the answers. Okay, class. So please not comment me because not giving the right answers. Answers in physics is not our aim. Our objective is to solve the problem. Just to remind that. To become a good problem solver is you have a step, a guide, or strategy to tackle the problem first. Yeah. Whatever come later, that will be what the answers. Yeah, the answers. Solution is the problem strategy. Yeah, in physics. Okay. Any questions? Ada soalan tak? Any questions? Class? Okay, kita take a break. Kita take a break. Yeah, since I don't want to we have some exercise soon. Okay. Boleh ulang jalan kerja nombor 2. Jalan kerja nombor 2. Apa jalan kerja nombor 2 ni? What is your mean by jalan kerja nombor 2? Okay. Maybe you want to know what is your problem tu kan? Your problem tu, how you tackle the problem. Okay. Okay. What I mean here is yang overflow. Yes. Okay. First one. First thing you need to tackle the problem is you use your main principle. What is your volume expansion? You mean that find first this one, because both of the solid, okay, the glass expand. So you need to find this the first one. Okay, all the value, all the quantities we know the value. You just substitute the value. Okay, the coefficient. The initial volume, both are 200. You can remain the same value. Okay, delta T is 80 just now. Okay, then you solve for the second calculation. Okay, for the Macri, similar equation, but now using different value. You have beta for the Macri. You can refer the table. The beta for Macri. Okay, the volume, initial volume, also the same. Okay, 200. Delta T also the same, is 80. Then you can get the answers 1 and 2. That is the fundamental based on the thermal expansion. And then it come what actually the question asking you to find out. Okay, so the strategy is based on the fundamental to find the thermal expansion, delta V, volume expansion, because we want to make it consistent. Both of them will having volume expansion. From the volume expansion, we'll tackle what we call as the overflow. The overflow will tell that the mercury is expand more than the glass. That's why the mercury is overflow, because mercury is remain in liquid form, right? As it expand, it will overflow due to the it having delta V that is larger than delta of the glass. That's why I want you to compare both calculation, number 1 and number 2. So how to find the overflow? Due to the difference between the two values of expansion, mercury and glass. So you deduct the value of the mercury and the glass so that you can get your answers. Okay, that is my how to get the answers. If you get 2.7, you're correct lah. Katakan jawapan betul lah. Or if you get 2.7, okay, fine. Because sometimes given answers pun, sometimes not all of you get the same answers. Importantly, to make yourself confident to find first the expansion, because this is the fundamental of the thermal expansion, or what we call volume expansion. Okay. That's my kita punya discussion. Kita akan proceed with next discussion on what we call thermal conductivity. Okay, class, kita take a break for 5 minutes. Okay, takes 5 minutes from now. Okay. Okay, the second part under the chapter is what we call as heat transfer. Okay, this is not the second part, it's the third part, right? We have the first one we discuss on what we call temperature, and we complete thermal expansion. Then we get into the third part, heat transfer mechanism, heat transfer. Okay, so what actually we say about this one is because we said just now for the rod, okay, for the rod, okay. So once we apply heat, we don't discuss yet this heat quantity. We say that it will expand with delta L. Okay, so what actually happened? The temperature that we see here is will increase. Usually we say expansion is a positive expansion. Okay, I mean that it will become longer. Okay, from the initial L naught. Okay, okay, so it become longer. So it become T to T naught to T. Okay, so with that for this expansion of T. So we say that if we okay, if we heat up this metal, this solid, okay, the heat will transfer in with that with some what we call as some rate, some rate that call after this is what we call the dynamic of the heat. So they will like, you can think of like the heat is in motion, like what we call as our velocity, okay, the velocity. So that's why we call in our discussion after this what we call the thermodynamics. So the heat is not I mean fixed. We will move throughout the medium. Okay, in our case it's solid just now. Okay, through the rod. So we need to determine what we call as the dynamic of the heat. So this is what we call the heat transfer. Okay, the term heat transfer, and we will discuss three kind of conduction, three kind of mechanism, heat transfer mechanism. Okay, so we have conduction. Okay, the first one. Okay, we have the second one, convection, and the third one we have the radiation. So we have three heat transfer mechanism. And actually we already discussed. This is for the solid here. This is what we call by conduction. I mean that within the medium, okay, once we apply heat, okay, the heat will conduct. So we have what we call a conduction. So this is the first type. Already we look after that for the expansion case. Okay, so then we will discuss also convection. Conduction is mainly in the case of our solid. For the solid, okay. When it comes to convection, okay, this convection it will apply to liquid and gas. Okay, liquid and gas. Okay, liquid and gas. Okay, so it apply to liquid and gas. Okay, so that what we see as by conduction. I mean that the medium that we discuss is now is for convection is liquid and gas. Okay, such as water, okay, or gas. Okay, in our case, mainly after this, when it comes to chapter 15, we use gas as a model. Okay, what we call thermodynamic of model using gas. Okay, we have by convection. Then finally we have a radiation case. Actually, this is a special case. This is by radiation, what we call through without medium. I mean that this is can happen. Okay. Can happen without medium. This is special for what we call the electromagnetic radiation, EM radiation. Okay. So this is what I think we aim to complete our discussion. And most of the kita punya analysis of our quantity that we focus more in the discussion is case number 1 by conduction. And case number 3, so we did make it detailed. We don't discuss much on convection. So we will see after this for both cases, conduction and radiation. Okay, that is what we aim for this discussion. At least we can tackle this one. And the first one is this is what I mentioned just now. Okay, what we see the three cases, and the important is what we call as the rate of energy transfer. The rate of transfer is the heat energy. The Q is, when it comes to rate, we divide by time. So this is what we call rate. The term heat transfer is more on what we call the rate. And this is just a model to see how by conduction, okay, we have let's say case where this is in modern cooking hoop. I mean, this is the cooking because nowadays we have what we call induction cooker. Induction cooker. If I want to say this is a modern cooking, okay. Myself at home pun gunakan we use natural gas, okay. We use flame, we use the flame. But now let's say as a model to say the induction cooker, okay, is using radiation, because this is a kind of heat transfer to the your cooking let's say your bowl here, okay. So you can transfer the heat from the cooker, okay, hook to the cooker, the boiling bowl ni. Jadi you can transfer to the it's made from metal, but anyway it is by radiation. The heat will transfer to the metal, and what happened? The metal actually we conduct the heat through all the body, okay, within this cooking bowl, okay. Jadi you can feel the heat by conduction. Overall, the body that is made from a solid, such as a metal, okay. Even the handle can make from plastic, whatever, but still by conduction. But inside there's a water, and the water, okay, so you boil the water. So the water actually is within we get the heat from this bowl, okay, or you might say kettle, whatever, okay. So the water will transfer within it, okay, by convection. So this is just a model, just a model to explain how the three processes can happen during cooking process, during cooking process. Okay, we will make our discussion fast, okay. Okay, the first one by conduction. By conduction that we have here is to show some model. This is not really focused in our discussion. What we call the mechanics of the heat transfer. Okay, we look from the what we call the microscopic in terms of the molecules interaction. Okay, once we apply heat, so what actually is there will be what we call as the vibration. Once heat transfer at one point, so it will transfer to other molecules in all direction. It will transfer in all direction. Okay, so actually in our case here is one molecule heat, then another molecule will be transferred via collision. Sometimes we call it in terms of vibration. It will be vibrating. This you can think of, let's say you are in the room, or where let's say you are sitting now. Let's say there's no aircon, you are feeling hot. So now you are start to move around, because you're feeling the hot, the heat. So this is like what we call a vibration. So the heat will be transferred to others. So we can have what we call a vibration. So solid are good conductors as compared to gases and liquid, especially for metal. So for metal, this is mentioned here. Metal are a good conductor, since we have a reason for it. Because we can see from our expansion, metal having high coefficient of expansion. And then one also reason why metal are good conductors, one of the what we call the carriers, the energy are the electrons. The electrons is the carriers which can transfer the energy or the heat, throughout the medium, our solid. So it will get the solid become hotter, faster as compared to gas and liquid. Okay? So that is what we can say. The electron are the one that are responsible. Okay, when it comes to metal, okay, it has a lot of or what we call abundance of electrons. Okay, as a carriers. Okay, that's why we call a good heat conductors. And also after this, also as a electrical conductors when it comes to our future chapter on electricity. And one thing is there is what we call as a important on conduction. There must be a difference in temperature. Different of temperature. It means that once we heat here, so this is your T. Let's say because it's hot, you can call as a TH. And the other place should be having a different in terms of temperature. Should be a more smaller value of temperature that called TC, or cold temperature. Immediate, because heat will transfer from high temperature to low temperature. Immediate, yeah, it will transfer to other point that is having low temperature. Okay, okay. So this is high. It should be that way. Okay, so heat should have different in temperature. So it will transfer from high to low. So it is a thing of like potential energy. Okay, that's why we have high potential energy at higher level. So that it will be transferred into the to the low level as it falling down. This is what we can say about the difference in temperature. Okay, so that heat will be conducting in the medium. So once we understand that, okay, we want to further look the model for heat transfer mechanism. You can see in your text, I think. Okay, not showing this diagram, but anyway, this diagram is a model to state how heat is transferred in the solid. Okay, maybe yours dalam notes kita pakai ini kan. Okay, your case using this model, right? Model of something like this. Okay, you have like this. It's similar, but the model should have some area. Then you start to apply heat on the left. Okay, you apply heat on the left. This heat will transfer, okay, through our solid, to our solid from left to right. Okay, from left to right. Okay, so we apply here. Of course, here is a TH. Okay, because this is what you apply heat as a temperature from the source. Usually, when you say about heat, it always to think of a high temperature there. Then we have a TC, cold temperature. So it's very important to have these two quantities, okay, difference, so that heat will be transferred from left to right, okay, shown from the diagram. And we focus along the direction of X. This is what we call. Sometimes your text using L thickness, okay, is also equal to the thickness. But sometimes to show that it's along X, then we have some thickness. Especially when we say thickness here is when it comes to, let's say, a glass, on a glass window, for example. After this, we will learn on that. Why? Let's say you have a window. Well, you have a window, for example. Okay, let's say you are in the room there. So this is inside the room. It's outside. Okay. So maybe I can make it the other way. Okay. So I can say like this. So I want to have the one similar like the one that drawn here. So I want to say this is inside, this is outside, okay, of the room. Is so where you have the sun, for example, outside. So it's hot. So this is TH and this is TC. So that's why we want to say about the thickness of the window. Okay, so we can have what we call delta X, thickness of the window. So the heat will come from out into from out to in the heat will flow. So there will be what we call Q over T, and this is the window that made from glass. Okay, especially okay, we want to know how thick the glass should be, so that you can control the heat flow. Okay, so this is the idea. So anyway, we have all this quantity TH, TC, and we have the thickness of the window. Okay, then we have some area. You mean that we have a 1, 2, 3, 4 quantities, and we'll be able to write down our heat transfer in form of this equation. Okay, as I told, there will be Q over T. Okay, with time. So we have all the four quantities. You have the area, where the heat will pass through. The difference in temperature, TC minus TH minus TC, so usually we call it as a difference in temperature, delta T, hot minus cool, always that way because heat will transfer from high to low, and divided by L, you can put L or delta X, it doesn't matter, usually in our case here, using L, okay? Then we have area, then we have one constant that called thermal conductivity. In that a given material, there what we call as a constant that called thermal conductivity, okay? Given by material, so we have conductors that having good conductors should have high K values. You can refer in the text. Okay, in your text, I think you can have these K values. I think, at the back, we have two table there. Given a table, you can see that metal there is at high K value. This equation is very important. We use this one. Important to see that higher the area of exposure of the heat, okay, it means that you'll be able to let the heat flow through the material. So higher area, so higher K. Okay, it means that higher K, it means that you can have also having the rate is higher. What happens if your thickness is higher? It will be oppositely. Okay, I mean that kalau your thickness is low, okay, so you can increase your heat transfer. Okay, it is inversely proportional as understood. Okay, so you can let's say you want to make it. That's why we put some tinted, for example, some layer, some tinted, okay, on the window. Okay, so that that tinted can reduce not reduce the heat. It reduce in terms of the heat rate. Okay, it make it the heat flow slower lah, in terms of not get it too fast. I mean that is, we can make it the heat slow flow of flowing into the room or into the house. So you make a tinted. That's why we call it tinted, to slow down the heat, but heat still get in. Yeah, and that's the fundamental where heat will flow from hot to cold. Okay, so or you make a thicker layer, you make some insulation. So sometimes we call insulation. Okay, you can slow down the heat flow. Okay, so you insulate it's insulation so that you can reduce the heat flow from outside. Such as importantly when it comes to ice, you say the ice in a box, in the box. So you want to avoid the heat from outside to remain the temperature that cool inside the ice box. Yeah, so you need to make it some insulation. Yeah, using some insulator. You put something of insulator with lower K values. You can see the table. I think you can refer the table where you can have all these things explained. Yeah? And where you can see that, as told just now, okay, metal is having high in terms of last time we understood is a high coefficient of expansion. But you can see here such metal also having high thermal conductivity as compared to other material that is a non-metal. It's very low. You mean that it's high. Metal is having high K. Okay, high K value. This is the K value. Okay, using K values. Okay, so you can see there. Okay, unit is also in Celsius. So don't worry about using your delta T. So you can use in Celsius. So if you compare to metal, okay, with non-metal, such as the one on the right here, such as you can see here is some such kind of non-metal. This is asbestos, for example. This is insulator. Is much larger, yeah, than this K for the asbestos. Yeah, this is some insulator. Okay, some insulator. Okay, but you see you discover some diamond. Diamond is having high conductivity. Okay, so very high. Yeah, I don't want to discuss why this thing happen. Yeah, diamond will conduct heat faster. So okay, because the light and radiation can pass through diamond fast. Yeah, a good term of absorber. So anyway, this the thing that I want to highlight, yeah, such a metal, yeah. So you can compare the gas. Gas is not really the conduct the heat, yeah, heat transfer as compared to metal. By the way, we see of this, we are using some example for that. Styrofoam is also another kind of insulator. This is a good insulator. So this is what we call insulator. Insulate. That's why we call insulator. It is a good heat insulator. Both of these. Okay. Also glass. Glass. You see glass? It's also glass. Also it's lower. Okay. I don't want to use a diamond. Maybe you'll be question on that. And wool. There's a wool there. Also another kind of insulator. It can reduce the heat transfer. Okay, look, a problem. Okay, yourself clear on this. Class, are you there? Still there with me?
There.
Right. So you see, there's a formula given there. On another formula, it's same formula. One is Q over T. Maybe you discover in your notes another one, yeah. Also similar. Both are similar. Both are similar. Okay, you don't worry on that. But you're using P there because when you divide Q over T, delta T or delta T is a time interval. Okay, during the heat transfer process. Okay, this is a unit of joule. Okay, because it's energy. There is a time, second. If you look, this is the unit of watt. Okay, watt. Okay. So this is a equivalent what we call as a power, of a power unit. So heat transfer is the unit is a unit of power. Heat rate. So this energy rate. So the unit is also can the heat power. So in thermodynamic, we see as a heat power, heat rate. But we don't say power because much on thermal. By the way, it's a similar using having watt. We want to have some exercise on that. Okay, we look on a problem that is given in PBL. I will say about there's a what we call a condition that call multiple layer, such as like this. When we have a conductor that is what we call a multiple materials like that given to you, what we call in series. This is the common one that a problem that we use. You have two material, number one and number two, connected, joining together. Then we apply heat, that we call TH and TC. Okay, one is having K1, one is having K2. Okay, so heat will be transferred from hot to cold this way. It is the heat rate. Okay, so what actually we will discuss after this in the PBL. Okay. So what actually how the equation looks like, there will be some equation given here, but anyway, I don't want to use much equation. The fundamental is the what we say just now for a single material, but this now we can have what we call a multiple materials, and this is already we'll discuss about our insulation case. We put a tinted so that we can reduce the heat transfer. Anyway, we see first the PBL what happened, and we are also having such kind like this in parallel, but this is a another type, one we call series, one we call parallel. We see these two together after this. Okay, I want to hit with your PBL. Okay, your PBL something like this. Okay, something like this. Maybe look something that not really good to see the writing there. I want to show mine first. Mine first on the model. Can you see my screen, class?
Boleh.
Yeah, this is the case. Okay, I want to show this one. Okay, your problem on PBL 14.4. PBL 14.4, something like this. 14.4, something like this. Okay, you have two material. Okay, one is called as copper. One I can put copper first. Then it welded, it means that it joined. join with brass, I call B, brass. You put in series. So this is what we call series. Okay. Okay. So it's saying that one is the dimension is given there is a bar. It's a bar. When it comes to bar, it is a rectangular. Okay? It's a rectangular shape. Okay. Something like this. It's a bar. That's what you call chocolate bar. Chocolate bar is something like this. Okay. So you have the area there. Your area. Okay. In terms of the square. Yeah, this is the square given by 2 times 2. 2 times 2 in terms of centimeter, right? 2 times 2. Okay. Same cross-section area for both copper and brass. And the length, each one is 10 centimeter. You mean like this here is 10 centimeter. All are using using 10 centimeter. Okay. You can refer same length. Okay. Same cross-section area. Okay. To make it that way. And you're saying that you read carefully. Okay. The two ends of copper and brass there. One is that if I say at the over there is copper in a steam bath. So this is what we call a steam bath. A hot one. A steam. Okay. This is what we call at 100 degrees C. The steam bath is 100 degrees C. And this is a cold one. It's saying as in the brass there is ice bath. It's ice. Okay. Cold one. Ice is to make it 0 as a standard. So you have different of temperature between them. Okay. Our problem actually when we discuss on our equation, okay, our equation is given by just recall back, okay, that one, okay, QOT. Okay. For a single material, QOT on a single, you mean that kalau you want to find your punya QOT, the formula is, you know well, is a K A delta T. It's a very simple one, divided by the L. Okay. So, kalau you want to solve this problem, okay, you need to solve one by one. For the first one, you find Q1 over T1. Okay. So for the copper, let's say copper is number 1. So you apply the formula number 1 for copper. Okay. This is for the copper. So you put K for copper, A for copper, okay, is K1, right? A is the same for both. So delta T is L, this L1, okay, it's 10 centimeter. I let you to do yourself, but come question, what is your delta T number 1? Okay, because delta T number 1, okay, because it joined at somewhere in between here. So I may call here is a T at over here is using A. Okay, but you want to use A, it doesn't matter. Okay, let's say I want to call A. I prefer to use another symbol. No, I want to use another symbol. Usually we call as a join point. Join. Okay, so I want to call as a TJ. Join. Okay. So you mean that delta T1 is where we have a junction here, J, join there. So delta T1 you can write down as, okay, is equal to, because heat flow from hot to cold, okay, so J should be lower temperature because heat will flow from left to right. You can see the diagram is from left to right, so you can put as a TJ, TH, we know the value is 100 minus TJ, but the TJ down is unknown. But this value is something that is not given in the problem. Okay, class, hopefully you can get me that one, right? So we have the unknown, what we call the TJ, because it will question you what is that value there. Okay, you may expected the value somehow because it is a bit between 100 and this connection. I mean the joint is from 100 to 0. So of course this TJ should be somewhere in between. Yeah, this TJ, the temperature, it should be in between. Okay, 0. Okay, okay, and 100. Oh, no, not that way. Sorry. This should be less than 100, higher than 0. Okay, so it be in between of 0 and 100. Okay, but we need to find what's TJ, and you do the same for this one for brass. You can fill up similarly. Okay, this is for the first one. You do the same. Now it's K2, L2, all the same except K1 is differently K2, right? You do the same. Delta T for number two is should be what? Plus. And then we can tell me should be what? Number 2. If you follow me, anybody can tell me what is your T2? You want to write down like the first case for copper. So what should be delta T2? Just respond me. Are you there, class? What should be your delta 2? Should be written. Something to put there. TC plus TJ. Okay. Why you want to put TC plus TJ? Because we see that heat should flow from high temperature to low temperature, and the heat flow is from the left copper to the right brass. So as I told, TJ is somewhere between 0 and 100. So the term should follow the same thing. Only thing is now you did TJ should be somewhere like this. It should be higher than, and the end up should be your TC. Okay, because TJ is higher than the ice. Okay, so it should be different in terms, because the term delta T here is different. So TJ is higher than TC. That's why heat will flow from left to right. So delta T2 should be this form. Okay, so please to highlight this one. But TC, you know well, is 0, right? But anyway, I want to highlight this one because sometimes not always to be 0, can be any value that lower. So the junction is having a temperature should be within 0 and 100. Okay, between the two temperature there. Okay, so the unknown is TJ, the problem, and we have a Q2 and T2. And very important when it comes to connection like this in series, we join like this, continuously like this, with condition that having the same cross-section area. Okay, although with this different of material, the heat rate in series always to be equal for both. You mean that if you want to say this one as a general one, as Q over T as overall, you mean that for 1 and 2, 1 plus 2, you mean that if you say this one, to be like this, I can write down this one. Okay, it with some term. Okay, this is actually for from TH. You mean that this is from TH to TC without J there. Okay, and you may think of some equation after this. This is the equation can be written as something like this, because both of them, you have a formula combination like this, should be like this. You have A, similar you have A there. You can refer in the notes in your module. And actually this one delta T here is not T1, T2. You can combine, you can just proceed with the TH minus TC. That is your ice one, and this is equal to 100. Of course, this one is equal to 100. Is overall for 1 and 2. And actually, what happened to your K and L? Okay, this is the concept where in series, there's what we call something like this. Okay, you sum, this is what we call L over K. For the first material plus the L over K for the second material. This L over K is a layer term where where we add up in this manner. Okay, so actually this is a if you want to know as overall. But anyway, this value Q over T for overall always equal to the Q1 over T1 for the individual one. But anyway, we can solve the problem to find TJ. Okay, I want everybody to tackle this one, the one that in the box here, so that you'll be able to get your what is your TJ. As in your module, you get the answers there, 78, right? You get this TJ is equal to, you get what I mean by how to solve the problem, you get 78. But you need to show first this one, okay? Q1 over T1, put all the values. Okay? You have the term that TJ, the unknown. Then you put all the values for the term for TJ for the for brass. Okay, and you'll be able to tackle to get your TJ. Okay. After once you get your TJ, you can start to calculate what is Q over T. Even that it will have both Q over T, or the heat rate should be the same for both number 1 and number 2. And also, you'll be able to prove this term also equal to the one that with individual one Q1 over T1 using the TJ values. Okay, so this is the one that I will say about what we call as the temperature at the junction. Okay, class, any question at the moment? Ada soalan tak for the PBL 14.4? Any questions? Any question? Huh? Tak ada? Okay, tak ada. Good. So I want everybody tackle the problem. You need to show this one first. Write down the value, this equation, plug in the values. You will leave only TJ. Okay, this is the first equation. The first equation. Just to highlight back, this is the second equation. Similarly, same for technique where you have for number 2. So you have the second equation for brass. So you have the unknown that called TJ. Just to highlight, the first copper you have TH minus TJ. H is 100. Okay, always 100 minus TJ. But this one, T2 is, TJ is unknown, but TCH is 0. You need to know that this is a 0, right? This is 0. You mean just having TJ. So you equate Q1 over T1 equal to Q2 over T2. You'll be able to get your TJ, that is a 78. And you'll be able to prove mathematically you get your TJ. And I want you to find what is your heat rate. The question is not asking on that. What is your Q over T1? What is Q2 over T2? Both should have the same value. With that, you need to find what is your Q over T1 values. I want you to find this value. Right? This is for number 1. What is the value? Once you get your TJ. And this Q over T1 is equal to Q2 over T2. Okay? So you will be able to get what is the heat rate for copper, what is the heat rate for brass. Of course, both should have the same answers. And you apply same thing about the values, but now for overall. 1 plus 2, you can use this formula because this is the note given to you. If you have a 2 joining, you can use this method where ignore the junction. You can have your value that also having as Q over T for number 1, Q over T for number 2 should have the same answers. You mean that this should be consistent. So please find this value. You mean that you can confirm your answers for the 3 values. Okay, fit this one. And the unit is watt. Okay, or joule per second. Okay, this one short form lah. I mean short method. Short method, you can get your Q over T for overall. But this value also need to be known that also equal to Q1 over T1 and also Q2 over T. But you to confirm yourself, you use the TJ values. Okay, for both 1 and 2. Okay, so that is what we call the heat transfer in series. Okay, directly using to metal and always equal. I mean in series. Okay, kalau tak ada soalan, try that one. And finally, the question. Kalau you look the question. The question here is how much thermal energy? Okay, how much many in per minute? Per minute here is 60 seconds. Your calculation that I asked you to find just now is what we say as Q1 over T1 after you get your TJ. Okay? You find the let's say this is your TJ there. Let's say there's a TJ, even if you get your TJ. Okay? Once you get TJ, you find your Q1 over T1, or you can find your Q2 over T2 for number 2. Okay? And this also equal to Q over T. It should be equal. You can try yourself using the equation that using L over K. So this T is for both 1 and 2, as I mentioned just now. Okay. Once you get this one, this is actually the unit is the answer is joule per second or watt. You need to find this one. What is the value? Yeah. Once you get your TJ, then even to know about 60 seconds, you just multiply all this value. You can multiply this value with 60. Okay, because it is will give you this per second is per second. You'll be able to get that is for 60 seconds. This is your answers for 1 minute. For this is to solve number 2. B there. Okay, so more energy will be transferred for in terms of time. So your calculation is based on per second. Okay, hopefully you can follow up to this point to get the idea of heat transfer by conduction. Okay, class, is that clear? Is that clear, class?
Clear.
Okay, we take 5. You try to prove your TJ there. If you get 78, and after this I will look through. Kita tengok dalam your SCL. Okay, nanti I just show you. We will see exercise. Okay, kita ambil exercise. Okay. There were question on something that I hope you can see my screen. On this kind of problem on conduction. But now is what I mentioned just now. Okay, you can see number 6. Okay? Number 6 and number 7. Number 6 is quite similar, like the one that I say, like your PBL, copper and aluminium in your SCL. Okay, but the question is not like the one that's saying you to find your junction. But anyway, you need to look similar approach to tackle number 6. You have copper and aluminium. Equal diameter, join at the end. Join together in series. Okay, you can tackle number 6. Okay, and number 7 I will discuss after this, where you have a case where not as the one that we use like the 2 rod different metal connected joining at the end. But number 7 is the real situation that I call as an insulation window. So you have a window. So how you can tackle the window problem with some insulation. Okay, this is we see after this number 7. I think number 7 and number 8 will have the same thing, the same approach, where we want to see some seal ataupun some insulation, so that we can reduce the heat transfer. Okay, you can see number 7 and number 8 both are similar approach. Okay, but we will discuss after this. Yeah. Okay, we take 5 minutes. We have some exercise. You can try. I will end up the program within half an hour after this. Okay, take 5. Okay, see your SCL in your web assignment. Okay, both is a case for window. For window, the window having what we call a rectangular 1.1. There's answer there. No mind. Okay, you have as I told just now with my case of series, a series of case by the in and out. Okay, you can have your tinted whatever on the windows. Okay, so this is just without with tinted. The first one is a window pane without the tinted is 0.62 thick, and ada thickness ada. Jadi outside is 21, dan sebelah dalam is 0. Ini macam apa memang sorry, terbalik kan. Indoor is 21. Ini yang dalam panas. Luar sejuk. Ini like apa winter someplace. Okay. Not in our case. Luar sejuk. Dalam panas, kan? Jadi the heat will get out from the inside into outside, right? To outside. Jadi there will be a temperature different, 21 degree C, kan? Ini tempat ini lain sikit, kan? Luar heat is getting out from the room, outside. Okay, so calculate the heat rate. Heat rate, I think you can do yourself. Q over T, kan? So you have your K for the glass. You can use your glass K. Then your area is given by 1.1 times 1.8 meters squared. That is your area. Delta T is 21. High is 21. Low is 0. Divided by what? 0.62. This is a 0.62 centimeter. Ini in centimeter. Kalau meter, kalau soalan betul lah, you gonna 0.62, you divide by this value. Look your SCL. You can try this. This one is straightforward. Okay. This is a B there. You can see the answer is in what? The B there is in 1 day. 1 day. It means that 1 day ni tadi 60 minutes. 60 for 1 minute, kan? Now is for 1 day. So one day, kalau you want to use for the first one is 5370 for 1 second. So 1 day you can get for 1 day in second. You can find out 24 hours, right? Not for 1 minute. For 1 day. Try to confirm the answers. Of course, the answers there is a power 8 joule. Ini is a high value sebab dia 1 day. Okay. So this is what we call the energy loss through the window. Quite similar like our case study, tapi it's for 1 day. Okay, that is should be understand. Number 7. Number 8. In number 8, okay, I think I have a question also yang number 9. Number 9 pun sama. I give some idea of to take your consideration to look the problem. Okay, sama. Number 9, 8 and 9 sama. Cuma I want to say about number 8. Number 8 here is ada mention there is a 2 glass pane. We call a thermopane windows. It means there is some insulation. Ada 2 glasses. Tapi you have a seal layer air in between. Maksudnya ada 3 layers, 2 layer glass. Okay, in between ada air. Okay, kelas you ada glass, tapi in between the 2 glasses, okay, ada air in between. Seakan-akan ada 3 layers. So now come question. Macam mana you nak want to calculate? Okay, you punya what we see as a heat transfer in what there. So you see there, the area of the window are given dah calculate. Cuba thickness is 0.5. Okay, macam mana you nak calculate this calculation? You mean that you have a 3 layer. Tapi sebenarnya this is the thickness here is sebenarnya is you multiply by 2 kan sebenarnya. Tapi kalau kalau because both are same glass, jadi you kena gunakan L over K. L1 over K1. Kalau 3 layer maksudnya L2 over K2. Tapi since the glass is same thickness, you can combine together. Okay, so you be able to find this is what we call a series. What we say as a material. 2 glasses and 1 and there's a medium that called air. Air berapa nilai K for air? Plus cuba tengok dalam modul, what is the air thermal conductivity? Please respond. Apa air? 0.0256. Okay, you are following me, right? So maksudnya kalau soalan ni kalau you want to tackle, okay, seakan-akan ada 3 layer lah, Tapi kalau you want to combine, is it you can do the combination, but actually you can combine these two. Okay, you can combine. Yeah. Anyway, you try to find. Are you getting your answers as in your web assignment? Yeah, your web assignment. This is my answers there. Okay. Then katakan you want to have a multiple glass. Okay, of course you can see the value there. Okay, multiple glass akan reduce your punya. Okay. You want to compare with multiple glass tapi tak ada air layers. You nampak multiple glass is 1 cm. Tadi is 0.5 cm thick ish. Tapi katakan you want to use a single glass tapi multiple. Kan? 1.3 meter. 1 cm. Just 1 cm. Dia bukan thick tapi sebenarnya 0.5 now become 1. Sekarang is a 2 glasses. Tapi the first one, the 2 glasses, they separate with the air. But now is a 1 cm. No, we don't have the air layers. Okay, you nampak tak? The answers there, you mean that kalau you can consider glass tu individually. You nampak? The answers is differently. Okay, so please try to get the answers with the air layers that is in between. So the first one is L1 over K1, L2 over K2. There's air layer. Then L3 over K3 are the 3 layers. So I recommend that you split that glass together rather than you combine. Kalau you combine, seakan-akan macam like one. Maybe you can try yourself. Let's say you combine. You get same answers. Okay, apa differentnya? This is something I want to share with you. Your assignment, your assignment for this thermal conduction. Okay, I think that's clear, kan? Boleh Alright. Plus, any questions? You get the idea of this, what I'm saying about the insulation. Okay. Masa kalau tak guna thicker glass pun is still higher without the air in between. The air will help to prevent the heat. Okay, any question?
Tak ada.
Okay. Little bit kita proceed. Tomorrow kita akan having discussion on what we call bioradiation. I want to just go through je. So I want to stop quick. Ini I think is by convection. By convection, I don't discuss detail. Just want to go through so that we can stop our discussion for this discussion for heat transfer. Okay. So the second one is by heat transfer through convection. This is we will not discuss as the analysis such as by conduction. By convection, you can read yourself. This is straightforward. Which actually is applied for gas, liquid and gas. Okay, such as you have the one that you are boiling the water. Why the water become hotter? Okay, within the air, the liquid. So by convection, this is water. The liquid, water. You are boiling the water. Where actually the principle is we can have by heating. Actually, by convection, there's a two type. There's a two type. Okay. But the principle is are the same. One is called naturally convection. One is a force. You mean that naturally convection is such as due to not using energy. The one I show to you, okay. In our case here, okay, you can see natural here. Okay, this is like boiling water. So boiling water is a natural case. Is the one that convection is the standard one, very simple. You mean that the hot one akan get up. You mean that the hot one at the bottom you heat it, getting up. But the cold one come down and cool. So this is what we call as a natural. By you are boiling the water. This is due to in terms of the density of the molecules. You mean that yang high density, low density getting hot, so the atom become far from each other, so it will will be moving up due to the high density is a in terms of density is a high density. In terms of hot is a low density. Yeah, in terms of the molecules. Yeah, so that this is what we call the natural due to the what we call as a in terms of okay, what is happening. Okay. Okay, this is due to the what we call the density. Yeah? So this is what we call natural convection during boiling. Okay, the forced convection is this is like in the case of yang required some energy or force. So that's what we call forced convection. We require some energy. Usually we call a pump or mechanical force, such as refrigerator. How we cool your in the freezer. Okay, in the freezer. And I don't want to discuss this one. It's using a pump. Yeah. By the way, this is have some explanation further, but at least not as usual one. And one thing about natural convection, force when come to for at the house, some house, what we say is a pump, like in this way. This is we use forced convection. Yeah, using some pump ini untuk heater at the house. Satu lagi, kalau you notice some kind of kalau your text kalau say over there, okay, yang at one kind of natural convection here is like macam at the kita punya at the sea kita punya at the beach at the beach kan, you feel some cold and hot, so there's some kind of convection there. Kalau sun heat the sand, so the heat will getting up, then we will have a cold air. So natural convection is a principle of what we call as she's saying that it's a boiling force, but I don't discuss on that. It's based on density. So this is in boiling water is a natural, but if using some force, it's called using a convection due to a mechanical system, such as in the freezer. Okay, because freezer usually yang sebelah atas tu is cool, kan? Yeah, you mean that is cool on the top. That's why freezer is standard is cool on the top. Yeah, so hot at the bottom. So what happened? The air will flow down. Yeah, sama juga, tapi the idea is by force. But actually the idea is something. This is what we call using force convection. Okay, anyway, kita tak discuss detail on this, but we have the second case. You can read yourself. Tomorrow kita akan discuss what we call heat transfer by radiation. Yeah, this is very important to us. Okay, so this is we have some concept or law behind of the heat transfer by radiation. Yeah, by convection, we don't discuss the analysis. We understood this is due to the some heat transfer due to the condition of density, different between hot and cold. Okay, that one is kita boleh end up lah for the chapters. All right, you boleh tengok the problem from the SCR for the web assignment. Okay, class.